on by. Of course, I've been talking for a bit, but let's get going from the current slide. Okay, the 1, 2, maybe just one major announcement I need to make sure you know about. Student course evaluations are now open. Have you done them yet?
I forgot about it.
Okay, yeah. Just get them done anytime between now and the end of the term. But don't forget about them permanently. I value those for myself, but also for the instructors that are under me, and also the other groups on campus that don't have direct interface with students so much. They need to know what kind of job they're doing too. So please do the student course evaluations. All right, then let's talk quickly about today. We're going to continue. Well, double the class size, triple the class size. Wow. Okay.
You know, I got an overlap class.
Yeah, I know.
Morning class lasts out 15 minutes.
Right.
Later than your class starts.
Okay. And Dart is here. Okay.
Wouldn't miss your class for anything.
Oh, unless it was important.
Yeah.
Oh yes, all right. Yeah, you must have a dull life. Okay, never mind.
Everybody else must be eating.
I guess. Yeah.
Oh, man.
You wish you could eat, huh? I can hear the stomach.
I'll take an order for you.
I was just talking with Samuel about what today is going to be, and we're going to continue in chapter 6. There is an outside chance that we'll finish chapter 6 today because we've got 2.5 hours. I think we will finish chapter 6 today, which I didn't think we were this far ahead, but I think we...
How many hours?
2.5 hour class and 2 hours left. Well, it's not that now, but it's
Well,
close
you
to
said 2.5 hours. I got happy.
Yeah.
I thought you was talking about 2.5 hour class.
Yeah.
Man, he's trying to get that good evaluation.
No, I wouldn't do that. Okay? All right. But today we'll have class for the 2.5, and then we'll do the lab on Ohm's Law, which I think all of y'all are going to do quite well on. And I doubt if it'll take you your full 2 hours, so hopefully you will get that done. So if we do finish the chapter today, which I think we will, that means Monday we will be in chapter 8. We may even start chapter 8 today. I don't know how far we'll...
Going from chapter 6 to 8.
8, yeah. Chapter 9 is on, is that light or something?
Skipping 7.
Yeah, skipping 7. Yeah, 7 is light, and we just didn't have time to get it done. And chemistry, this is supposed to be physics and chemistry, so we have 5 chapters on physics and 1 on chemistry. That's physics and chemistry. So what it looks like to me, we may get started on 8 today. So then we'll have the Ohm's Law lab today, and then if we do finish the chapter today, Tuesday, we will continue in chapter 8, but only for 2 hours, then have the last chapter 6 lab, which is electromagnetism, and that'll be 2 hours, and then 30-minute test on chapter 6. And then on Thursday of next week, we'll continue chapter 8, probably finish it, and we only have 1 lab for chapter 8, so that will probably be Thursday of next week, which runs us, well, we may not finish the chapter, then I think we will, but that means we've got class on Tuesday and then the final on Thursday. So what we'll do in class on Tuesday of next week is, I'm sorry, we already talked about Tuesday. The Tuesday of the following week is basically have your chapter 8 test that day, and that will also be the last day to turn in stuff, because that day I'll be turning stuff back to you. In fact, today I can turn some stuff back to you. Finally, everybody finished test 1 and 2. So let me get these. Yeah, I know. Pretty sad, isn't it? Here's your chapter 1 test. Or give Samuel his. And here's your chapter 1. 2. Last person turned that in as well. So here is chapter 2. Your chapter 2. Your chapter 2 test. And right here, I'll give you your chapter 1, 2. So I already passed this out.
Yeah, they like to score on that one. You kind of keep it if you want.
What's that?
They like to score on that. You kind of keep it if you want.
No, what would I want with a score like that, huh?
Right.
I'm not. Okay. Let me get you marked present. We now have enough for a bridge table. Okay.
For what?
A bridge table.
A bridge.
Yeah. Okay. All right. As I was saying, okay, a couple of things. I said this earlier to Samuel, but the others weren't here yet. The student course evaluations are open. So if you haven't done them already, anyone done them already?
Complete.
Oh, you have. Fantastic. If you haven't done them already, please do them between now and the end of the term. It's okay to wait till the end of the term, but please don't put it off and forget about it, okay? If you're likely that to happen, go on and do it now or soon.
Evaluation?
Yeah, student course evaluation.
All right.
Oh, you have? Good. Okay.
Sure.
How long did it take y'all? 2 of you have done them.
Well, actually,
They don't
my
take it.
evaluation, they got quite a bit of questions.
Yeah, they did
I
that.
say about 15 minutes.
Yeah, probably get them all done in about 15 minutes or so. Okay. All right, please do those. And then as I was saying before, what we're going to do today is continue in chapter 6, probably finish chapter 6, okay? May actually get started in chapter 8. Then the last 2 hours we'll have the lab, Ohm's Law lab, going to be old hat to most of you. And, sorry, something in my tooth. Can't get it out. Anyway, so we'll do Ohm's Law lab. More than likely, you'll be finished before the 2 hours is over, and you can probably leave a little early. That means on Tuesday of next week, okay, you'll have, we'll finish or continue in chapter 8. We may not finish it. That'll be for 2 hours. Then 2 hours of the last lab in chapter 6, electromagnetism lab. And then we'll have the test on chapter 6, 30 minutes. Then Thursday of next week, if we haven't finished chapter 8, I think we probably will finish chapter 8 and have, if we do finish, we'll have time to do the lab for chapter 8. Which then leaves us with the following week. We're supposed to have class on Tuesday and then the final exam on Thursday. Actually, I think this is ridiculous, but I've seen them do it before. Okay, Alfred's here. Now we have enough for a basketball team. Okay. Okay. Get this passed out to Alfred. After a while, I'm going to quit doing this and just tell you come get it through. Test 1 and test. Okay. Now, so, and by the way, please do, if you haven't already, do the student course evaluations. Okay. So today, probably finish chapter 6, maybe start chapter 8. Then the last 2 hours will be the Ohm's Law lab for chapter 6. That'll be it for today. Next Tuesday, continue chapter 8. And that'll only be 2 hours. In 2 hours, electromagnetism lab, the last lab for this chapter, and then 30 minutes test on chapter 6. All right. Then Thursday of next week, if we haven't finished chapter 8, we'll finish chapter 8, Then we'll do the lab on Chapter 8. And then the following Tuesday is supposed to be the last day. Now, actually, I saw this on the calendar this morning because I was trying to get it right in my head. They say on the calendar that we have class Tuesday and Thursday of that last week, and then have the test on Friday. Yeah, that's what it says on the calendar. Not going to happen this way. We're going to have the final exam Thursday of that week. Now, but all that being said, oh, and by the way, your research papers are due sooner rather than later. Okay, please get those in. Samuel sent me one email. Was it today or yesterday? Yesterday. Okay, I saw it today. So I will accept them that way, but be sure that everything looks good to you. That I checked his and it did look okay. I haven't graded it yet because I didn't have a printer. But if you don't have it into me by that following Tuesday, that last Tuesday, not this coming class, next Tuesday, but the following Tuesday, on that day I'll return everything to you. If you haven't done a lab, haven't done a test, gonna be too late. So get everything in. Okay, thanks. I would appreciate it. Okay, so and have all labs caught up and all tests caught up, preferably sometime next week, because they're all going back to you that Tuesday. So that's the drop dead date on that. Also, your papers are coming in then, and if they're not in, you'll be losing points for being late. Okay, so that's that Tuesday. And then we'll probably have the test on Chapter 8 that day. Now, that just leaves the final exam for Thursday, and that will not take long, okay? So, be thinking about how you want to handle next week, that last week, not next week. We know how next week's going to go. One possibility, and this could give you an extra, you get to drop one lab right now. This will give you a possibility of dropping a second lab if you choose to do this. If we have time, which I think we will, that last Thursday, and possibly, last Tuesday, possibly even next Thursday, a week from today. But if you want to report on your paper, you can have an extra lab score. If you do a report on it, you get an oral report, you get 25 lab points. So you can drop the lower if you need to. If you don't choose to do that, you don't have to. Okay, so that will be part of, could be as early as next Thursday, but more likely the following Tuesday. And then I will give I think we'll be finished so you can do your Chapter 8 test that Tuesday. If any of you choose to, it's not required, but if any of you choose to go on and take your final that day, if there's time after the reports on the papers and stuff. If there's time after you've done the Chapter 8 test, if you wanted to do the final exam, I'll let you do that. If everything runs smoothly, we'll see. But I think there will be time, and that way you don't have to come back on Thursday just for that. But I did want to plan one of those 2 days of that last week, either Tuesday or Thursday. So let me go on and order pizza, and we'll have pizza before whatever else happens, test or final or whatever. Would you rather have that the Tuesday or Thursday? But we got all next week to think about it, so we won't worry about that today. But just see. If you don't want to do it, we don't have to. But I know you don't get to eat in between. You don't get, huh?
You know you won't do it.
Yeah, I know that. That's why I said yeah. What's that?
Is our final going to be like on all of the like bits and pieces of every chapter?
Yes. It's going to be, I can't remember now, something like the top 3 or 4 issues in all 6 chapters. You hopefully will have all your tests back by then. So you already got your first 2 back. And
so we'll be able to use our tests?
Not use them, but you can use them to review. Okay, now you can write a formula and equation sheet for the final as well. Okay, Mason's here. Okay, so you will have that as a possibility too, your formula and equation sheet, which you can base it on your test, if you choose, however you want to do that. Okay. The last person did turn in test 1 and 2, so I'll return those Now, that's one. Okay. All right, and please do your student course evaluation. Have you done that yet, Mason? Student course evaluation? Not yet. Okay, please get those done sometime. And what we're going to do now, continue in chapter 6. I'm guessing we're probably going to finish chapter 6 today. We may start in chapter 8. Okay? Then, after we do that, the last 2 hours will be your Ohm's Law lab, which I don't think any of you will take 2 hours to do, but it does take a while to set up, so we'll get moving on that. And then Tuesday of next week, 2 hours more of class on chapter 8, 2 hours of lab on electromagnetism, and then the test on chapter 6 will be Tuesday of next week. Then Thursday of next week, if we still have some more to do in chapter 8, we'll do that. And then I think we'll finish the chapter that day, so you can have your lab that day. And then if anyone wants to do a report on your research paper, you can do that if there's time. And it's optional, so if you oral report on whatever you do your research paper on. If you do that, you get a 25 point. If you do a presentation, you get 25 points, and you get to drop the next lowest grab. You already get to drop one lab score. That will give you an opportunity to drop the second one. If you don't do it, you don't have to, but then you only get to drop the one. You can if you want to. I'll leave that completely up to you. I'm not going to require that, but let's see, did I mark? Yeah, I think I marked Mason. Yeah. All right. Any questions before we get going on today? Okay. Now, we are on somewhere around page 156 in my book. Other of you, your text may be a different page number. We were talking about the sources of the magnetic fields. Someone remind me, what are the only 3 elements that are naturally occurring magnets? Say again? Only 3 elements that do exist as naturally occurring magnets. Not all of the elements, of them would be, but that when they are, they're the only 3 that are naturally occurring magnets. Huh?
The type of metals that are
3 types of metals. Boy, we went over this several times. Iron.
That's the 3 that's right next to each other.
They're 3 right next to each other.
I'll tell you.
It's in chapter 8, your periodic table. Before that, or after that? Yeah, I think it's the other side. Past that. That's chapter 8. There it is. There's a big one somewhere in there. There it is. Yeah. 3 metals. Nickel, iron, and cobalt. That's it. The only 3 naturally occurring magnets that exist now. They may have been able to manufacture some others from alloys and stuff, but those are the 3 naturally. What's that?
That's what magnets are made out of?
Yeah, and those are the only magnetic materials too, naturally occurring magnetic materials.
How do they make electrolyte?
Wrap a wire around it.
Well, I know that, but
Yeah, we'll talk about it. That's coming up in the day. Yeah, but good question.
On is off.
Yeah,
Like you ever went to
those are called electromagnets. Exactly.
You ever went to like
Yeah.
scrapyard. They got them-
Yeah, exactly. Exactly.
There's nothing else that
That's naturally a-
made out of?
Yes, naturally occurring magnetic materials. Only those 3 elements: iron, nickel, and cobalt. Now you can have alloys made up of them, but those are the only 3.
That's all the stuff they'll stick to.
That's what?
That's all they'll stick to.
Yeah, exactly. Naturally occurring magnetic materials: iron, nickel, and cobalt. Of course, iron is probably the most common metal on the surface of the Earth. In the Earth is the most common metal in the earth. Nickel in the earth is probably number 2. On the surface, nickel, there's not as much nickel, but deep down there is. So yeah, we're mostly an iron planet and an iron universe almost, and there's a reason for that, but that's in another course. Okay, so those are the 3 naturally occurring magnetic material. Why? What is the source of their magnetism when they're magnetic? Not all of them are. We'll talk about that too. The reason is, and remember, in just about every chapter now for the last several, we've looked at things macroscopically. In other words, that piece of thing is a magnet, okay? Or microscopically, on the atomic level, that's where we go to find out. There are microscopic fields, and that's why I think it's those 3. They're right next to each other in the periodic table. They just happen to be, their electron configuration lends themselves. There are what they call intrinsic spins of those subatomic particles. Electrons, not so much protons, but could be. So the spin of those particles. Now, electrons and protons in particular. What do electrons and protons have in common? They're in an atom, sure. They have charge. Is that what you said? Absolutely. Neutrons can spin all they want. Who cares? They don't have any charge with them. But protons and electrons do. So the intrinsic spin of those subatomic particles, electrons and protons particularly, and the orbital motions of the electrons around the atoms. Because, now we haven't actually physically said this yet, but let me say it now because it's coming up later too. What produces a magnetic field is a moving charge. What produces a magnetic field is a moving charge. So if you have the spin of these charged materials within the atom, or the orbital motion of electrons around the atom, that's what gives these microscopic fields. And iron, nickel, and cobalt are the only 3 that have them. All the rest of those elements in the table, their spins are all over the place and their orbits are all over the place, so all the fields that would have been there cancel each other out. But iron, nickel, and cobalt just happen to have residual magnetic field that the other elements do not. So that's what's happening on the microscopic level. Every iron, nickel, and cobalt atom has either certain intrinsic spins about electrons or protons, or the orbital motion of the electrons in the atoms that give it what they call a magnetic moment. All right, Jeremy's here. All right. And by the way, the last folks that have come in, before you leave today, I've already passed out to the ones earlier. The last person did finish their test 1 and test 2, so I have those papers to get back to you today. So don't leave home without them. Okay. So on the macroscopic level, the macroscopic fields, we're going to talk about each of these. Permanent magnets. Okay? Yes?
The 3 metals you said naturally magnetic.
Yeah.
Why you have 3 pieces of metal and they don't stick together?
Okay, we'll get to that, okay? I promise, we're going to get there. And it's coming up really, really soon, okay? It's going to be here, okay? So we have permanent magnets. Now, these could be naturally occurring permanent magnets or permanent magnets that have been made by man. And we'll talk about both of those possibilities. The Earth itself is a magnet, a big magnetic field. That's why a compass works, because the Earth has a magnetic field. Okay? And you might say, why? I just sort of gave it away. What is the number 1 occurring element in the entirety of the Earth? Iron. And number 2, metal? Nickel. Both of those are naturally occurring magnetic materials. So no wonder the Earth acts like a big magnet. Most of it's made out of magnetic materials. Now, the other thing that creates a macroscopic field, and Kemp just said it, electric currents. When you have an electromagnet, you've made that with electric current. And that leads to electromagnets. So these will build on each other and go. So let's start with the permanent magnets. And here, I hope this will answer what you were just going to ask. Make a battery out of it?
Yeah, you know what I'm saying?
Yeah. Maybe not a battery, but a generator, maybe. But it'd be a pretty weak one, okay? And we'll talk about that too. I don't mean to be putting you off, but we will be hitting that very topic, okay? Or at least close to it. First, what are our three ferromagnetic materials? Nickel and cobalt, exactly. These ferromagnetic materials have what they call an atomic magnetic moment. What that means, either the electron-proton intrinsic moment or the electron orbital motion. Okay? Remember, what is it that creates a magnetic field? A moving charge. A moving charge creates a magnetic field. Okay? So if those electrons are moving around, well, electrons move around every atom. Every atom. Okay? But they move randomly around most atoms, so they don't create a magnetic field. But on iron, nickel, and cobalt, the way the electron structure is and stuff, they do create that magnetic field. So every iron, nickel, and cobalt atom has an intrinsic magnetic field, an atomic magnetic moment. However, most iron, nickel, and cobalt is not magnetic. It would be attracted by a magnet, and it is magnetizable, but itself is not a magnet, because most of the time, those magnetic moments are oriented just any way they happen to be, okay? Randomly distributed. Most of nature is random, okay? So this magnetic moment would be up, this one would be down, that would be right, that would be left, yeah, on and on. They're random, so they cancel each other out. That's
my question about why metal don't.
exactly. That's it. I told you we were going to get there. However, you place this same piece of iron, nickel, or cobalt with these little, they call them domains, okay? Place these domains in a strong magnetic field, and then they start lining up that way. And that goes to Camp's observation about electromagnet. Once you turn on or create that magnetic field, then these domains line up according to that, and that's why that core inside the electromagnet suddenly becomes magnetized. Okay? Now, not all of them do. Some are still randomly distributed, but more of them will point in the direction of that field. And therefore, it becomes a magnet and becomes magnetized. Okay? So the clusters of the atomic moments align in the domain and become magnetized. Okay? Now, when it's not magnetized, they're randomly oriented. They still have these atomic moments, but they're in all different directions. When they become magnetized, then more of them line up in one direction. The domains are aligned. The magnetized domains are aligned. Does that sort of make sense? Now,
You can also do that with electricity.
yes. Okay, and we'll get to that. Yeah, y'all are good today. Y'all are
You
seeing
pick up
this.
a screwdriver or something, wrap a bunch of wire down it.
Yeah. Exactly. And we'll get there. Okay? Let me give an illustration. And this actually did happen to me. I think I talked earlier in the term about the house that we moved into and the work I did in the backyard and the digging of the patio, all that kind of stuff. Before we started that, I think I went into this as well, there was a privacy fence between our house and the next one, but it just picked up, and it wasn't in the best of shape. It picked up, our garage was here, and then there was a shed behind the garage. And the shed was literally falling apart, rotting. It was in really bad shape. It was almost dangerous to be in. And it was leaky and all sorts of things. And then from the shed, they went the privacy fence back to the corner. But, of course, when we bought the house, they had done a survey, and I noticed that the stakes for the survey were about 4 feet out from where the privacy fence was. So I talked to the lady next door, and she was renting. I said, did you know that, that is actually our yard, and you've been mowing our grass for it. Thank you very much. But she hadn't. But and she said, yeah, I think my landlady knew. And she went and talked with the landlady. They lived in Tuscaloosa, and they came back and said, yep, she knows that they just put the fence there. But yeah, part of this is your yard. And I said, okay, as long as you knew that. Well, I knew I was going to have to tear down the old shed. It was just in miserable shape. And since I was going to tear it down anyway, and the privacy fence wasn't in great shape either, and since I was going to do that, I said, well, I think I'll move it back to the property line. And she talked with her landlady and came back, sure, absolutely. That way we don't have to mow it, So, yeah, that wasn't their issue, but just to get it back where it belonged. So I proceeded, and it just happened to be our house sits facing pretty much due south. Okay, so in the backyard, that's due north. Okay, so I went back and I could get those fence materials in 8-foot sections. Okay, that whatever you call that board, the fencing. So I measured it all, found out how many posts I would take, and dug the post holes. Boy, it was one hot, dry summer. That was a clay hill and rocky too. And basically, I could only get a few things down with a post hole digger, and had to stop, pour water down that little bit of a hole, let it soak in a while, and then dig some more. And that's how I did it. It took me literally days to get those post holes dug deep enough for it. Okay, and then got the post set. Got them fairly aligned. Ran a string. So I make sure the posts were where it was. So I was going to have this first one dug. I had the other corner post. I was going to line up the others in between. So I went to nail that. It was sort of over my head because down at the bottom and nailing the thing here. And I'm not a very good nailer either. And after a few blows that way, the nail came popping out. And I reached down and went looking for it in the grass and stuff like this. I just happened to have the hammer hanging in my hand as I was looking for the nail. Huh? No, the nail stuck to the hammer. I said, what? Okay. That wasn't a magnetized nail before, I don't think. The hammer wasn't magnetized before, I don't think. Why did that become magnetized? Say again? I was striking it facing almost due north. So I was aligning the vibration when I hit that nail. Like I said, I did hit it a few times. These domains started aligning themselves, not on a magnet, but on the Earth's magnetic field. And they started aligning themselves. And then when I reached down, it attracted to the hammer. And the hammer probably got aligned that way too. So sure enough, you can take a randomized one, and if you perturb those domains enough in the presence of a strong magnetic field, and the Earth's magnetic field isn't particularly strong, but I was facing due north, so that made it even better. I made that into a magnet. Okay, for what good it did. But that can happen. So, the Earth's magnetic field, let's talk about that. It originates deep beneath the surface of the Earth. Now, what is it that creates a magnetic field? Moving charges. Now, how can there be moving charges deep inside the Earth? There's iron and nickel in there, but why would charges be moving? I mean, there's charges moving everywhere, but why would they be moving in an orderly fashion? Well, do you know anything about the structure of the Earth? Okay. Okay. We live in and on this very thin crust. And that can only go a mile or two deep, which is really deep, but that's the crust. Inside the crust, there's another part that's called the mantle. It's also solid. It begins to be a lot more iron in the mantle than is on the crust. There are certain places where there's plenty of iron on the crust. Birmingham, Bessemer, Pittsburgh. There's areas where there's more iron near the surface, but most of the time the iron is deeper, okay? Really deeper. Well, that's the mantle. And basically most of the Earth is the mantle. It's big, thick layer, and it's heavily iron, but it's solid, rock. But inside that is the core of the Earth. And there's actually two cores. There's the outer core, which is so hot because all the pressure of the Earth's magnetic field pulling down has the weight of all that crust, which isn't much, and the mantle on that, and the pressure pushes those things tighter and tighter together, and the Earth is moving and spinning, it melts the inner core. It's probably very similar to the mantle, but it's melted. It's a molten core. So here is a solid rock Earth spinning around a molten core, which doesn't really spin as much. It spins some, but there's no reason for it to spin. So you have these surfaces moving past each other, and guess what? They knock off electrons. So you have electron motion as the Earth spins, which creates a magnetic field. A moving charge, the spinning of the Earth, the molten core of the mantle, that creates a field. So the originates deep beneath the surface from currents in the molten core. Now, inside the molten core, there's an inner core which becomes solid again. Just so much pressure on it, it forces the liquid back into a solid. So you have another surface there that you can have interaction between the liquid and solid. So there could even be two. So but in that molten core, that's where you have the current. Moving charge induces magnetic fields. So the weird thing about this is, what do you call the point on the magnet? The North Pole. And where does the North Pole point toward? Okay. It points to a South Pole, doesn't it? So that means that really the northern pole of the Earth's magnetic field has to be a South Pole to attract the compass needle. Or else we should be calling the pointed end of a compass the north seeking pole that seeks the North Pole of the Earth. But most people just call it north, which makes the Earth itself a South Pole up there. And, yeah, everything is sort of backwards, you know. And this wasn't Benjamin Franklin's fault. You know,
And we live up north.
okay. Now, what's that?
He said we live up.
No.
You mean down north?
Okay.
Yeah, we live down north.
Down north or up south one, I don't know which, okay. Because you always hear people, are you from down south? No, I'm from up south. Okay. The actual North Pole isn't quite at our geographic North Pole. It's a little off. And when I say a little, it's not really very much. Right there is the North Magnetic Pole of the Earth. There is the geographic North Pole. So they're not far apart at all. Pretty close.
And somebody found that because they had a compass that went.
Probably, yeah, and it went bonkers there. It wouldn't.
That's the wrong place to have a compass that crazy.
Yeah, it is. It's not, I wouldn't want to. If I want to know where I was, I would really want to know where I was when it's that cold. Now, surprisingly, the South Magnetic Pole is quite a bit further off, and I don't know why this is. I've got to find it now.
So the Earth perfectly round.
No, the Earth isn't perfectly around. Okay, we are sort of, they call us an oblate spheroid. Okay, whatever that means. It means we're sort of like a pear, sort of like me, a little thicker in the middle and not. Yeah, never mind.
He said
What?
they call us like another planet calls us.
Yeah, yeah. Oh, look at them. No, all of the planets basically. No, none of them are really perfectly spherical. I don't think. Actually, the gas planets would be closer. Why can I not see the South Magnetic Pole? I found it many a time, but I cannot see it now. South of Australia, not that. Oh, there it is. There it is. I just got to turn far enough. See, there's the South Magnetic Pole. See how much further that is away. So, no, it's not. Things aren't quite like you would expect. But anyway, that's the difference there. Because, yeah.
How do we know it's a molten core?
That what? A molten core?
How do we know?
Okay. It's basically because of earthquakes. Okay, this is a strange way to say it, but it really is. Because when you have an earthquake or an atomic explosion or anything like that, we don't have many of those, hopefully. North Korea. Okay. We don't, when you have earthquakes, they send off what they call seismic waves. That's how we know there's an earthquake. Okay? There are two types of seismic waves. One is a pressure wave, just like sound is a pressure wave. You can feel the pressure. It's a longitudinal wave. The second is a transverse wave, which is one that goes like this. Think of that hose lying on the ground, and you do this to it, and you see the waves go like that. With a transverse wave, the motion is up and down, but the wave goes that way. With a pressure wave, the pressure is this way, and the wave goes that way. Okay? The pressure waves travel a little bit faster than the other way, the sine waves, the transverse waves do. So they can track them separately, and they always, the pressure wave comes in first, and then the transverse wave comes in later. But a pressure wave, think about this, sound wave being pressure wave, does that travel through, it travels through solids, it travels through liquids, and it travels through gases. That's why I can talk to you, you can hear me, right? Because the pressure wave is moving through a fluid. A transverse wave will not go through a liquid or a gas. Well, when they track and do the measurement of these waves, let's say, pick a place for an earthquake, any place, name a place. San Francisco, okay? We're going to have an earthquake in San Francisco. Okay.
The other side of the planet, they can't.
Okay. Over here and here and here, everyone sees both waves. Down here, they only see the pressure waves. That means somewhere in the middle of the earth is liquid. Because the pressure waves will go through, transverse waves will not.
Unless it's something we have to remember.
No, we haven't gotten there, and we won't probably ever get there, but we do know from the evidence it has to be there. It's the only model they can come up with that would block transverse waves that would block. And not only that,
That's why I prove it, too.
until someone finds some other reason that would do it. But yeah, that's what it is. But the other reason we know it's liquid, ever heard of a volcano? That's liquid rock. It's coming from down there. Okay, it's coming from somewhere down there. So yeah, there has to be liquid somewhere in the interior of the earth. Okay. So there's a fair amount of evidence. Okay. Now, so the magnetic north pole of the Earth is really a south pole of the Earth's magnetic field in order for compasses to point toward it. Okay. Now, because the placement of the north pole, north magnetic pole, is not in line with the geographic north pole, now it is in line someplace. Let me see if I can line this up for you. There's the geographic north pole. There's the north magnetic pole. Look at that.
This is really trying to point south.
Well, it's pointing two directions. One is pointing north, one is pointing south. They're pointing toward the magnetic north pole and magnetic south pole, though. That's right.
Magnetic north
Okay. However you want to phrase it, one's pointing one way, one's the other, pointing toward the opposite pole of the other. Okay. So whichever way you want to count north and south, they're just opposite each other. So we just happen to use north and south.
Our compass had hands like a clock. It didn't point past the center. It just pointed from the center out.
Got it.
Which way would the compass point?
Well, the north-seeking pole of a compass points toward magnetic north pole. The south-seeking pole of a compass points sort of toward the south magnetic pole. Okay? And I say that sort of for a reason. Okay? So we'll get into that. So here we are in Birmingham, Alabama. Okay? If you have a magnetic compass, which way is it going to point? If I'm facing approximately north, right? So which way would it point? Would it point that way?
It should point. It depends on where you are in relation to the magnetic.
Right, exactly. Okay. I'm here in Birmingham, Alabama. I'm
What's the
standing
magnetic
here.
north is?
North magnetic pole is right up there.
So we pretty much in
We are
line.
pretty much in line. We're only off by a little bit. But, to answer the question, and this is where the sort of comes from, which way is the North Pole? If I'm standing here, the magnetic North Pole, that's generally north somewhere there. Which way is the North Pole?
Past magnetic.
That way?
Energy.
No, the North Pole is that way. Well, because I'm standing here on the surface of the Earth, if I point that way, I'm pointing out in space. The magnetic north is here. It needs to be pointing down. And the component horizontal is pointing north, but actually, if it was free to float in 3 dimensions, it would be pointing that way. Therefore, the south would be up in the space somewhere. It's the north winds. We're closer to it. If you're in the southern hemisphere, the south is pointing that way, and the north is
Somebody
pointing.
asked me how to get to California. I was pointing in this direction, but I was pointing down, right?
Actually, if you're absolutely true, that would be it. But they're going on the surface of the Earth like that. Okay, I don't know that for sure, but I bet you they would travel on the surface. Shortest distance would be to go. Now, California is a big difference because we're on the same side. But if you're going to China, shortest distance would be straight through. Of course, you'd never make it, but you know.
Yeah,
But
you
that's
run
the
into
same.
that hot stuff.
Yes, you hit the hot stuff. Okay, that doesn't exist. No. Okay, so that's why we have magnetic declination. That's the offset from where you are. And as you pointed out, we are pretty much in line. We're not off much at all. Go a little further west and you're just in line. Okay?
So somebody here probably marked the North Pole.
What's that?
Somebody in America probably marked the North Pole.
I don't know. I don't know who
We're
did.
gonna make it easier.
Yeah,
for
make
us.
it easier
We're
for
gonna
us.
put it right here.
No, that's where it is. I'm not saying it stays there. It may wander a little bit too, depending on the verse wobble or other things like that. Okay, if you're over here in Maine, though, it's a little bit more different. Over here in Seattle, it's more distant. We just happen to be a place, yeah.
You couldn't really trust your compass.
Not
where
completely.
you're at.
Not complete. When I was in the Navy, and we were needing to, back then, you did your navigation several ways, but one of the ways we shot the stars, we shot the sun at noon, and you know, we did a lot of things like this to confirm where we were. And what you had to do first was figure out approximately where you were and figure out the magnetic declination, because that's going to mess up with everything. That's that little bit of an offset that you are, and depending on where you are, we had tables of those. We had approximately idea where we were, got the declination, did all that into it. Okay, so that's your offset. The direction of the field. Now this is the part I do not understand at all. I have a little bit of a theory in the back of my head, but that's about it. The direction of the field has periodically reversed itself. Now that makes no sense to me at all.
That's total hearsay. How did they know?
Here's how they know, since you asked. Because they drilled down and taken cores, and okay.
They had 2 North Poles on a piece
No,
of
okay, no, okay. Let me go to this one. Before we go there, let's do this one. Here is the declination curve. There is 0 right there. Almost going through Atlanta, not quite Atlanta, yeah, but somewhere there. We're over here, so we're off just a little bit, less than 2 degrees, or right around 2 degrees off. But in general, you're pretty close, okay? Up here, 22 degrees off. Over here, 18 degrees off. So yeah, there is an offset. We're pretty lucky that we're in the range, pretty close to where that is. I want to get that out of the way first. Okay. All right. So let's get back to your question. Why are there naturally occurring magnets in the first place?
the moving charges in the metal in the earth.
Okay. But why isn't all the metal in the earth magnetic? All the iron, nickel, and cobalt? It's not. Most of it's not. Okay? It's sort of like that nail I was banging on. If I had been banging this way, and I should have been facing this way. If I had been facing this way and hitting on it, If I'm creating a magnetic field, it would be going across the nail like this, and that would be very strong. So, when you have volcanic activity, and most of that lava is iron-based, right? It's pretty black, dark, iron-based. So if that is laying out in a direction aligned with the Earth's magnetic field, then that could be a magnetic material. When it solidifies in the direction of the Earth's magnetic field.
You built your fence on a fault line.
Well,
I know about to come up.
So this does happen, and now this is getting a lot deeper than what I intended in today's class, but it's still true. In the middle of the Atlantic Ocean, there's a rift, and it's spreading apart. The Atlantic Ocean's getting a little bit bigger, the Pacific very slowly.
That's all the continents were connected. You can see the outline.
Yeah. Exactly, that's it, exactly. This used to be in here, or they think it was, and you can find, they have mapped it. There is a ridge that goes almost straight up here. In fact, Iceland is on that ridge. It's a volcanic mountain that's on that ridge, okay? So, on either side of that ridge, you have lava coming up. It's probably coming up right now. It's at the bottom of the Atlantic Ocean, so you don't know it, but it is. It's bubbling up somewhere just about all the time. And then it's solidifying, sometimes fairly quickly because the water's out there really cold, and if the Earth's magnetic field is going along the north-south line pretty well, like that nail was, then it's forming naturally occurring magnetic material. Well, that's been going on for probably hundreds of thousands of years now, maybe even longer than that. So it's been laying out layer after layer after layer. The deepest layers are the older ones, the surface layers are the more recent, right? They've taken cores of that, and sure enough, they'll find, and let me see if it's on here, I think it's in another chapter. Yeah, it's way past here. But you got the small book, right? Okay. If you know someone who took the previous course, the Physical Science 111, it's in mine. I'll show it to you if you want me to. They have done cores, and they'll find some cores, the field lines are pointing north, sometimes pointing south, and then deeper north, and it just keeps on going down. I think in that chapter it said they poured down far enough and found 22 reversals. Now, to me, in my mind, why? I do not know, except possibly this. In between that were times when the Earth's magnetic field was not very strong at all. And you being an electronics type person, what goes in a pattern like this? AC goes in a pattern like that. So when it's strong up here, you could probably have strong field lines here, but if someplace later it goes down here, it's going to be along the opposite direction. So my guess is that the Earth, and why I don't know, as it does, it goes through cycles of strong one way, weak or not. The core of the Earth rotates? Yeah, that something like that is happening. It has to be, otherwise I can't imagine anything else. Now, I can't give you, that's it for me. That's the only thing I can figure, because there have been times in between when there wasn't. Fortunately, since man's been on the planet, traveling the seas and things like this, and found out about magnetism, we've all had a fairly strong magnetic field. We're still on this part up here, but I think if I remember what I've been reading, it actually is getting weak.
So, like, they don't know when it's going to work.
And it's going to actually go away, and then after a while it'll get weak again. We're going in the opposite direction.
780,000 years, I think we're pretty.
Yeah, we're safe. Okay, we're safe. Yeah, and we probably are going to destroy the planet before it changes again. So who knows? Okay. But yeah, it's pretty amazing when you think about it. But they have drilled down and found that the Earth's field has changed by different layers in the Earth's surface. And in between, there's places where they're just deposits that weren't magnetized at all. So I think that must mean those were the times when there was a weak, very weak field. Okay, let's move on. Electric currents and magnetism. I've already given this several times. Moving charges, which are currents, produce magnetic fields. How do we know that's true? Okay? If you were to have a wire, AC or DC? DC. Why would it have to be DC? AC would be changing so fast you wouldn't even measure a current.
DC in one direction.
DC is one direction. So the wire, and they're showing this with the electrons up. That means the conventional current would be down, right? Now, if you point your right-hand thumb in the direction of conventional current down, then the magnetic field lines go around where your fingers point. It's called the right-hand rule. And that's why they point like this. So if you had a strong DC current flowing through this wire, and you place the compass here, wherever you place it, the needle would change and point because the magnetic field is changing. It's circular there. Another thing you could do, if you had iron filings, we'll do this in lab Tuesday, not this one, but we'll use iron filings there. Yeah, you can see the pattern show up, but it has to be a really strong electric current. And I don't like to make that stronger currents. I'm afraid someone's going to get burned or shocked or something like that. But you can. I've seen pictures of it, and you can do it with a magnet, and that's probably a little bit better. So anytime there's a moving charge, you induce a magnetic field perpendicular to the motion of the charge. Yeah, and this will overcome the Earth's magnetic field, that wire will, if it's a strong enough current. Okay? There probably should be another slide there, but I don't see it. Oh, wait. Yeah, it seems like it should be. Okay. The shape of the field is determined by the geometry of a current. Straight wire is going to produce a very weak field. If the conventional current is that way, the field is this way. If the conventional current is that way, and the electron is that way, then it goes in the opposite direction. Okay? And that's why AC won't work for you, because it's changing so fast there's no net magnetic field at all. What you can do is take that wire, and rather than doing a straight wire, make it into a loop. Okay? Like this. One loop here. Now, the electron field is that way, so the conventional is this way. Your finger goes around like this, all the way around there. And notice on the inside of this, the point is up. On the outside, it's down. So the inside is the North Pole. Outside is the South Pole. So the North Pole would be this way. That's one loop. Okay, very good. You're already jumping ahead. What if you have a lot of these loops? They add to each other. They call superposition. Okay? I'm sorry. Here's that same one we did. The North Pole would be pointing here, therefore South Pole would be there. Notice the field is always perpendicular to the current. Okay? Make more loops, and you just make that field stronger and stronger and stronger. Okay? Like this. And this, by the way, it has a name. Anyone know what this is called? A coil. It could be called an inductor coil. Usually it's also called a solenoid. That's what a solenoid is. It's a coil of wire. Isn't it?
Solenoid, so you put something in there that actually moves linear direction.
Right, okay. And that's what you put inside a solenoid, exactly. And that's what makes a mechanical switch, a controller, or something like that. That thing in there that adjusts with that. But again, here you have your current here. Now they show the electron flow here. The conventional current would be going this way. You've done around the coil. Okay.
Really, that would be a heater.
What's that?
That would
Well,
be a heater.
yeah, it would too. But you see, you got all these coils, and that strengthens your north field stronger and stronger in that direction, so that acts like a magnet itself. Now, you actually put an iron core in there permanently, not something you go, and then you have what Camp was talking about with electromagnet. That's exactly what electromagnet is. Basically a solenoid with a permanent iron core in it. Okay, so a straight wire, current loops leading to a solenoid. Okay, just talking about you. No.
I figured so.
Okay. Okay. So what's an electromagnet? That is a solenoid or a coil of wire with a ferromagnetic core. I say iron core, any ferromagnetic. What are our three ferromagnetic elements? Iron, nickel, and cobalt. Exactly. So any one of those three is a core you have. Now, the current carrying wire is wrapped around the core, and that makes the core a magnet when the current is on, and not a magnet when it's off. And that's why in a scrapyard, like you were describing, you turn the current on, you can pick up whole cars, or whatever. Move them where you want them, turn the current off, drop them right there.
That core was made out of one of those three metals, didn't hold a charge. You can magnetize a screwdriver and.
Yeah. Okay. Generally, what you take for that is while it's being magnetized, bang on it like I banged on the nail, then you can make it permanent. Okay. But as long as there's no perturbation of that to permanently rearrange those domains, they're going to go back where they were. So this whole like the spring loader, it goes this way and you go back.
So you magnetize a screwdriver and bang on it, it'll stay.
You can lose. No, you can either increase or diminish the magnet. Like sometimes with some magnets, if you drop them just wrong, you'll make them demagnetize. Okay, because if you perturb those with the axis not in the direction of the Earth magnet. Huh?
If you drop an earth magnet.
Earth magnet? The naturally occurring magnet? I think you could. I don't know. I've never done it, but I think you can demagnetize something by perturbing it. Or you can magnetize it by perturbing it in the direction of the field. See, the deal here is the core. As long as it's not being disturbed in some pretty major way, it becomes magnet, then goes back. Becomes magnet, goes back. So those domains are sort of like I said, sort of spring-loaded.
Can you magnetize a round piece of metal?
You can. Refrigerator magnets are. They're just very short magnets. They're magnetized this
I'm
direction.
talking about a round ball.
Oh. I don't know. Perhaps you could if you. Yeah, but it's doing its own magnetation now by the spin, what's going on there. That's what's creating the moving charge. So if you had something that was going on in there, yeah, you could. I don't know how to make that happen.
Make our own solar system.
Yeah, exactly. Okay. I can't. Maybe somebody bigger than you or me can. Okay. All right. So the field is enhanced by the combination of the core and the current carrying wire with the wrapping. Okay. Now, what would happen if you wrapped half the core one way, but then turned it around and wrapped the other half the other way? You cancel it out. Yeah. This one's going this way, that way. You cancel out. So make sure the core is in the same direction. And electromagnets, as you said, can be turned on and off. I don't know. I've not been down there to see it, but I've seen pictures and I've heard people talk about it. The trucks on the expressway carrying goods, a lot of them are going down to Mobile. What's happening to them there? Loading on a ship. How do they do that? In the old days, they had to take straps and disconnect that cargo thing, strap it on, make sure they got the balance good, lift it, and it was a dangerous occupation. Now they do it with the magnet. They have all this being a magnetic material. Pick it up, set it down, turn it off. Nobody gets hurt. No loads start falling around. You don't have to hope that the strap doesn't break on you and stuff like that. Electromagnets are used for that, but not just there. Electromagnets are used in all sorts of things. There was a digital meter we used, but we will actually use some analog meters where the needle moves. Why does the needle move? Electromagnet is in there. And depending on the strength of that electromagnet and the motion, that gives you more or less current, voltage, ohm, resistance, whatever you're measuring. Microphones, speakers, just about every telephone. You know, the old ones, you know, that had the little holes in this receiver. Y'all remember that? No, y'all wouldn't. Yeah, some of you may remember. Yeah. Those.
had cords on them.
Oh, no.
Yeah.
I also had one in my truck. Ooh,
With a cord.
It was like a 90.
Yeah.
You had
Okay.
a bag phone?
Yeah.
I had one. It did work.
Yeah. Yeah.
Man, personal.
Okay. So every one of those has electromagnets in them. That's how sound is transmitted. Let's see. I think they have a thing. Oh, here. Let's start with the meters. Electric meters. Okay. Somewhere in there, you have a power supply going here. By the way, DC has to be DC. Okay. It's going around, a coil around, and there's a spring on it to give a little bit of resistance here. And by the way, this is all housed inside a magnetic field. There's a strong permanent magnet there, a horseshoe magnet here, north here, south there. Which direction does the field line goes here? Between north and south, which way do they point? Field lines. We talked about this. Okay? No, away from the north toward the south. Field lines are always away. You picture a little compass in there. If you put the compass there, it would point that way, because it points away from north toward the south. So therefore, that's the direction of the field. Always north to south. So you have a strong magnetic field this way. Okay? You have whatever you're trying to measure is here. If there's no current there, it just sits. If there's a little bit of current, then it tries to align itself with the field lines here, so your needle moves. And if it's very strong, it moves that way. So what you're measuring the current, or you're measuring voltage. If you flip it around, you're measuring the resistance, because remember, resistance is inversely proportional to current or resistance. So your meter goes the other way then. You flip a switch to do an ohm meter, and it just changes the field up. But that's exactly what voltmeters, ohm meters, yeah.
How do speakers work?
Speakers?
Yes.
Okay.
I don't know that. But what I'm saying is you got two wires. The two wires go to a speaker.
Yeah. Okay.
Hey, how about you be quiet?
Right here. This, well, here we go.
Hey, explain something.
Okay, here it is.
That's one of them phones you were talking about.
Yeah, exactly. This used to be what they call a telephone, people. Okay. Okay.
You had to dial. You couldn't text on this phone. You had to,
What? You mean they didn't have jitterbugs back then?
Yeah, but that was a dance back then. No.
Okay.
Okay. Here's what happened. When you talk, if you hold your hand in front of your mouth while you're talking, you can feel little pressure waves, can't you? Okay, those are called condensations and refractions. Condensation and refraction. That's happening all the time. So as he's talking, these little pressurized pockets separated by depressurized pockets are going. They go through little holes on the phone, and in here is a diaphragm, and the diaphragm has in between it carbon granules that conduct electricity at different things. The tighter they're pressed together, the more they conduct. The looser they are, the less they conduct. So when these little pressure waves hit, this is conducting more electricity, less electricity, more or less, more or less. So you have a signal there, okay? And that signal is picked up, interacts with an electromagnet, and that's what sends the signal through the wire. Now on the other end, you have a permanent magnet here. This is your speaker, the one you were asking about. A permanent magnet here, and then you have a coil here. That's your electromagnet, or Yeah, and the thing is, the stronger the current coming in here, which is from the speaking here, the stronger that current is, it's either going to compress more or expand more. Stronger, weaker, and then it sends out through the diaphragm little pulses of sound. You do it. And the amazing thing is, not only does the sound come across, but the tenor of the voice is better formed. In the old days, you just yelled and you hope they could hear you on the other end. Now you can almost tell who it is when you pick up the phone. It's pretty amazing that they've got the electronics to replicate the sound almost the same.
Yes, it's pretty cool.
My father-in-law, I'm hard of hearing, y'all know that. He has a frequency, especially on the telephone. When I answer the phone and he's talking, it takes me. I know his voice. Who is that? Now I hear him all the time, but he has a frequency I just don't pick up well. So I told Karen, I think he's your dad, because his is not, because my ears are bad. But most people can tell the whole thing.
Cans on the string work.
Well, then the vibration is going down the string. You have to have the string tight, so that's a transverse wave going that way.
By the
It's
way,
not a
yes,
pressure
we
wave.
did play with those when we were kids too.
We did.
Yeah, we couldn't afford cans. No, I'm just kidding. Okay. All right, let's go back to this. But that's what the meters do. Okay? The magnetic field, and hence the reflection, is proportional to the current, so that changes the amount that the needle is moved. Now, so this is talking about an ammeter, because current is directly proportional to the field strength. Voltmeter does the same thing. Volts and amps are directly proportional. But with the resistance, you wire it the other way, because your ohm meter is going to go in the opposite direction. So basically, inside your electronics, you flip the switch so they still the needle will go in the same direction.
You check resistance power off, so it's using the battery in the meter.
Say that again? Yeah, right. Okay. Yeah, you have to have a power source there somewhere, but you're measuring the signal, not the change in the power. Okay. And then I think you mentioned switches, same type thing, a relay or a solenoid switch. These are both somewhat similar. They use low voltage control to control currents to switch the large or high voltage currents on and off. I can't see in this one. They put a new box in here, so I'm not sure how it works. But the old thermostats, that was what they did. They had in it a bimetallic strip that, as it heated, it would either increase the tension or decrease the tension. And you would have a pool of mercury in there. And when it tilted too much one way, that would turn on your system or off, which depending on the way, and the other way would turn it the other way. The switches would do it because you had, and this is what they're showing here, the mercury in the glass vial, the bimetallic strip, this is a heat sensor here. When that's tilted far enough, then that closed the circuit on a small current going through an electromagnet, okay? And that, if that was strong enough, just strong enough, it would pull this against the spring and it would close this bigger current, and that would turn your heat pump on, okay? So you had to have a small voltage source here, DC, to turn on your heat pump here, which is a big source, okay? Same thing does in just about every switch. Now, this is your mercury switch in a thermostat. Same type thing with a solenoid, a movable spring-loaded core. Iron core responds to the solenoid field, and that's what you said, the solenoid, something's going to move in and out of it. So your water valves, auto starters, I bet you, a lot of things with the VCR switches, anything that you're doing. I mean, think about it. I can remember when I was young, you used to turn on the TV by turning a switch. Don't do that anymore, do you? You press a button, okay?
And you had those things stick up back.
Yes, you did. Strange looking thing. Rabbit
Smack
ears.
them too.
Yeah.
I got that.
Yeah.
I had one of those.
Okay.
And the kids would have remote, hey, come here and turn this channel.
Yeah, yeah, exactly. You didn't want to get up. You wanted them to turn the channel. And that's how you did it.
You had like
Nowadays,
6 to choose from, like 3 or 4 sometimes. On a good day, you got 5.
yeah, I can remember
Back
growing
then.
up, it was 2.
No.
Okay, and then when we got the third one, we thought we were hot stuff.
And
You know?
TV went off too.
Oh, yeah.
Certain time when that no TV.
And there was other things when my mom would vacuum, you know, it messed up the TV. But
Or somebody in the neighborhood had a base station.
what?
CB base station.
Oh, yeah,
in the
yeah.
house.
Every time they clicked, you could.
Once upon a time, CB radios.
Yeah, we're big.
Hey, I got one of them.
They either had them in their car, truck, house.
Yeah,
Some people had the base station antenna in the backyard. It looked like a radio station in your house.
right.
Yeah, we had one of those before too.
So, anything that switches. But if you think about the buttons that control your TV and change channels and turn it up and down and stuff, what you're sending is a really small signal here, and it's controlling something much bigger. So it's the same type of setup here.
You know,
Okay?
since we're on TVs, you know when they switched everything over to digital,
Yeah,
where you can't use the antennas.
right,
You know the old antennas they went on the roof, that little
Right.
closed line.
right, exactly.
Those are HD antennas. You
Are-
can use those. They just relabel them now.
Right,
You plug those into a new TV, you pick up digital channels.
wow, okay, I didn't know that.
They
Uh,
just relabel it and remarket it because they make
Yeah.
it seem like they selling you something.
Something new.
And some people probably already got the old one up on
Right.
the house.
And I know my wife ordered, and we have on all our TVs now, one of these,
It's flat.
yeah, not flat, it's curved a little bit antenna, and it really does a pretty good job. I don't know,
I put one of the old style on the roof of my house. I
Yeah.
put up 38
wow,
free. But I still have my
yeah,
cable.
yes, exactly. So, and now we already showed this one, telephones, loudspeakers, including any kind of speakers, coupling acoustic waves to electric currents. That's what they're doing. The sound vibrates the carbon granules, changing the resistance here, and as the resistance changes, because you have a certain current coming in, that changes your signal going out, because where the resistance gets less, more signal goes, more. So basically you're carrying a signal there. The signal corresponds to the sound waves coming in. That's what makes its way to the other end. And then on the speaker end, the changing resistance varies the current. On the speaker end, the varying current that comes from that signal changes the field in the electromagnet, that's this part, moving the permanent magnet up and down, and when you move that, you send air vibrating into the diaphragm, and there comes your sound out again. So it's really just the reversal, acoustic to electric through electromagnet, and then the electric through electromagnet back to acoustic again. Electromagnets are all over here. The moving magnet vibrates the spring attached to the paper cone, producing the sound. Okay?
It'd be like your ear, wouldn't it?
What's that?
It'd be like your ear.
A year?
Your ear.
Oh, yeah. And your ear basically is doing the same thing. Very good. What's in your ear?
Your drum.
An eardrum. And also around the eardrum and in the ear canal are these little cilia, the little things, and as they move, you are an electric.
If you got any left.
Yeah, if you got any left, you got that right. You are an electrical machine. Think about it. You have little batteries, which are basically the potential difference between sodium and potassium ions. And that's a very small difference too. And that's what's throughout your nervous system. That's what sends the signal. So when I speak and your eardrum vibrates and you hear, most of you don't, but when that happens, you're then sense that. Your brain interprets all that. What you see, electrical signals. You're an electrical machine. What tells your arm to move? Electrical signal. You are an electrical machine. And all doing this. So certainly the sound part, but also the vision part, all of it. Okay. Boy, what a jump here. electric motors. Okay? What's that?
We just work with motors and motor controls
Today. Okay, so then you may be able to teach the class here. There is a concepts applied here, which is sort of an interesting one. And actually it was maybe on today's lab or last time's lab, I don't know, we didn't do it. But this is actually the case. If you take a lemon or an orange or a grapefruit or anything like that, yes, exactly. Push it, rub it, roll it, really hard so you break some of the membranes and have juice inside, okay? Stick a paper clip in one and a piece of copper in the other. You have two dissimilar metals, an electrolyte in between. You created a battery. A battery, exactly. Okay? They really didn't do much with batteries here. I wish they had. Do you know the first battery that someone realized they had made, but they didn't know what was going on? Have I told you that story yet? I don't think so. There was an anatomist, not a physicist, an anatomist, somebody studying body stuff, okay? His name was Galvani. He was Italian. He was an Italian anatomist, and he was studying an excised frog leg. You know what I mean by that? This frog had been dead for a while, stored in formaldehyde, which kept it from rotting, so it was there. And they cut the leg off the dead frog, and he was studying this, trying to determine where the veins were, where the arteries were, where the neurons were, that kind of stuff. But he happened to be holding it with a pair of metal tweezers. Let's call them iron tweezers. And he had a little probe there that happened to be copper, say, or something else. And when he went to try to separate something and touched it, the frog leg jumped. And he, cleaned his pants. No, I mean, he said, "What have I done? Have I discovered life? This was a dead frog. We cut the leg off of a dead frog, and yet I made it move. Have I found the secret to life?" Yeah, Frankenstein, exactly. He was really excited. But the more he studied it and tried different things, if he was holding wooden tweezers, nothing ever happened. If he was holding metal, iron tweezers and an iron probe, nothing happened. He had to have two different metals. That's what made it a battery. So what he did, he had just made a little battery. Formaldehyde was the electrolyte, sort of like sulfuric acid in your car battery, and two different metals, lead plate and lead sulfate plates, and that's what created the charge. And the charge is what made the muscle contract. No life involved there. Now, usually with mixed classes, I can ask this and at least get some correct answers for what I'm looking for. But with a class like this, the odds are I'm going to get the wrong answer anyway. Have you ever had a battery in your mouth?
No.
Yeah, I knew all of you were going to say yes, okay. Because you're a bunch of guys, you just can't resist something like that. But I'm not talking about a physical battery that you put in your mouth. Say again? No, I don't mean a real battery like that. Have you ever had a battery in your mouth? I bet you have. But then too, some of y'all young, you may not have. You know the chewing gum used to come in an aluminum wrapper. Did you ever stick one of those in your mouth and bite down? Or a piece of aluminum foil that you didn't realize was still there? You know what?
Your teeth paint that.
Okay.
Especially if you got a feeling.
Ah, you hit it right there. You had a battery in your mouth. Because the aluminum is one kind of metal. The filling in your tooth is basically a silver composite filling, a different type of metal. You bring those together in the presence of a good electrolyte, your saliva. You just sent a signal. It is a very uncomfortable feeling because you just sent a charge right through your nerve. Because guess what? Where your filling is, you're really close to the nerve. And you just sent a
Takes that
good
battery
charge.
right there, goes all the way around.
Yeah.
You ever get wisdom teeth cut out?
And so you just had a battery in your mouth where you realized it was hot. That made a battery. Two dissimilar metals with electrolyte in between. They did almost nothing with batteries, but that was it. Okay. Now we're moving to electric motors. This is the last part in 6.4. What an electric motor does is convert electrical energy to mechanical energy. Now, how does it do that?
Magnetic field.
What's that?
Magnetic field.
Yes, you got it exactly. There's a strong magnetic field between this permanent magnet here, North Pole here, South Pole here. Which direction are the field lines there? Left to right, right to left, up and down, down to up. What? Where's your field line there? Say again? No, away from north toward south. As if you had a little compass there, it's going to point that way. Yeah, exactly. Okay, it always points from north toward south. So there's your strong field line. Okay? Now, what you're doing when you turn on the current here, you have, and by the way, this doesn't have to be a permanent magnet. This could be done by this electromagnet or solenoid or whatever this is down here. That's what's creating that strong field. Now, you have here, and what they don't show is the axis that this is rotating around, but you have brushes around there. These are the brushes that you see. You don't see the others. And as you turn on the current, then, okay, this is a strong permanent field. The field line's going this way. You turn on the current through the armature, which has is also electromagnet. Okay, and the instant you do that, if the current's running one direction, that makes this the north and that's the south. What's going to happen then? Yeah, it's going to rotate counterclockwise, right? Because the north's repelling and the south's repelling, and this north's attracting here, the south's attracting there. It's going to turn that way. But just about the time it gets halfway around, then the brushes switch polarity. Because you have basically kind of like a split ring commutator in there, and they change direction. And then suddenly that's the south, it's over here, this is the north over here, and it keeps turning. And boy, they keep coming. All right. Terrence is here, and Terry's here. Terrence and Terry, okay. The T's came in together, okay. Now, I don't know if the others are coming or not. And that's what's happening. So every half turn, you switch sides, and then it switch polarity, and it keeps spinning. That's exactly what electric motor does. The current that goes in, there's your electrical energy. It comes out as mechanical energy, the moving part. Your string trimmers on your lawn equipment, I mean, just about everything. I mean, lots of things use it. Your starter motor on your car is exactly that, isn't it? Okay? You turn on a very small current, and it turns a pretty big engine over. Okay? And that's DC, right? Only way you can do electromagnets is DC. The field magnet is stationary. Armature is movable, electromagnet. Armature rotates by interaction with the field magnet. The commutator brushes, there's the commutator, and that changes. See, I guess this is supposed to be the commutator here, and somewhere here is a brake, and there, see, this is, say, the positive or negative there, whatever it is, and when it turns one time around, they flip again.
You have to reverse that long?
I guess flip a switch. I don't know what you mean.
You swap the
Leads on the.
armature.
Yeah, exactly. Okay, and you make it go the other way, and that's what your ceiling fans at home do. When you flip that to doing the other way, you just reverse that. Very good. Okay, and they keep turning that. So that's an electric motor.
So when you
Electromagnets intimately involved here.
When you get an alternator that goes bad, you take it back to the store to get a new one. All it needs is new brushes.
Yeah, generally that's going to be the case.
They hold them off now.
Isn't that the case in most starters too? Isn't it really the brushes that usually go bad? Not really. Yeah, it could be a capacitor. Yeah, it could be, certainly. What's that?
That was a little.
Yeah, could be a solenoid too. Okay. Now, let's talk about the next concept here is magnetic induction. Now, what did I say created a magnetic field? A moving charge. Guess what creates electric field? A changing magnetic field. You've got to have the change there for things to work. So, what? This is electromagnetic induction here. I think you mentioned inductor earlier. The causes is the relative motion between the magnetic field and the conductors. And actually, it's not so much the conductors, it's the fields. The fields are what governing everything. If you have a changing magnetic field, you're inducing an electric field. If you have a changing electric field, you have inducing a magnetic field. They go like this, hand in hand, okay? Off from each other, but they still are doing it. So the changing magnetic fields near the conductor is going to induce an electric current, okay? And here is sort of an example of this. If you have a coil here, say like a solenoid or something, a coil of wire here, the more wires you have, the better. You have a magnet out here, outside of the range here. If you were to drop that magnet, so remember the field lines of the magnet leave the north and heading toward the south, most of them are concentrated here and here. Almost no field lines in here, right? So these field lines cut through the core, and as they cut through, they induce a current. There is no battery here. There is no generator here. There is nothing but a coil of wire, and yet you see the ammeter move. Okay? Now, if you were to wait just a fraction of a second till the south pole moves through, then what happens? It goes the other way. Okay? And if you moved it up this way, so the south was moving up this way, it's this way first, and then if the north comes through, it moves back that way. Okay? That's electromagnetic induction. A changing electromagnetic field induces an electric current. Okay? Now, the induced voltage depends on the number of loops. And earlier you mentioned transformers. That's exactly what you have going on in a transformer, different numbers of loops on one side or the other. So the number of loops, the strength of the magnetic field, if this was a really strong magnet, it would produce more current, a weaker magnet less. If you had more coils there, produce a stronger current, fewer coils, less. And the other is the rate of the magnetic field change. If you take this magnet and lower it really slowly through there, you get, that's it. You let it go rapidly, much more stronger, because it all has to do with loops, magnetic field line, the rate at which the field is changing. That's what matters. Okay, for whatever reason, it's the rate that it's changing. Now, there's a little blurb here on a simple generator. And I don't know if this is exactly what it's talking about. I think it probably is. But I don't know if you've seen one of these. I've seen a video of it. I've never done one myself. You can have let's see, how do they do that? Have a magnet here. Okay, I don't remember how they orient it, and have a coil of wire hanging above the magnet. And you start that swinging like this. But that is also connected to another coil of wire over here, over another magnet. You start this one swinging, this one starts swinging. And that this has become a generator, and this is responding. That's become a motor almost, that kind of deal. So I think that's what they talk about, a simple generator, but you can read that and see it on your own. There is a good blurb here on the current war. Now this doesn't mean a war that's going on currently. It was back when electricity was sort of a new concept. Who was probably one of the most famous electrical inventors ever? Thomas Edison. You're absolutely right. Name a few of the things he invented. Edison. Light bulb? Phonograph? Record players? Just tons of things. I mean, he had, I think, thousands of patents, okay? He was quite an inventor, okay? He got one thing wrong, though. He thought DC was the only way to go. There were two other guys, and I know Samuel's heard of one of them. Who'd you write on? Tesla, okay? Now, they actually have named a car company after him, haven't they, or something? Okay, they named this after him, too. Tesla worked for Edison, and for a while, they got along pretty well, I think, pretty famously, and really energized each other. But Tesla was convinced AC was the way to go. And Edison was absolutely certain AC was way too dangerous and you needed to go stay with DC. Thought everything would blow up and explode and burn down if you used AC. There was another name that's a pretty common one, George Westinghouse. Heard of that name before? Okay. He favored the Tesla side, the AC. He was actually more of a businessman, not so much an inventor, but he bankrolled, I think, some of Tesla. Tesla split away from Edison, and actually Tesla's theories came out more correct than Edison. Edison created more, but he was it. Now, Tesla was actually from Croatia, and one year, it must have been 10 or 15 years ago, I was teaching, I think it was this course, to the automotive students, and one of the guys in the class was from Croatia, and he chose to write on Tesla because he was from a nearby town. Everybody knew Tesla over there. And later, I think he had a brother or a cousin that went through the program too. Okay, but anyway, if you haven't chosen a paper topic, there's 3 different names in there. There's also the war between the two, you might say, the arguments, the conflict between Tesla and Edison, maybe between Edison and Westinghouse. There's a lot of pretty interesting things to write on there. I'll let you decide that. Okay, so let's move on to generators. We've actually, just a short time ago, talked about something that was very similar to a generator. What was that? A motor. And actually, I don't remember the order of this. I think it was at a World's Fair. It may have been in St. Louis or somewhere, that someone was there demonstrating an electric motor. I think this was how it went. But the guy who was setting it up happened to wire it backwards and turn it into a motor, and they said, a generator, and said, wait a minute, or they were doing the generator and made a motor out of it. I can't remember which was the chicken and which was the egg, but that's when, by accident, someone discovered the other one, okay? So a generator is basically a motor in reverse. The structure is you have an axle, you did before, main wire loops, magnetic field. The axle is turned mechanically, producing electrical energy, whereas the motor, the electrical energy is converted to mechanical energy, okay? So, most of these are AC generators. If you see generator, think AC, alternating current. And why? Yeah, because one time around, you're going to change field every time around. And then you convert it to DC, okay? And that has to happen in every automobile engine, doesn't it? Yes, your alternator does it because your engine, to recharge the battery, you have a little generator in there, right? But it is not DC. Can you recharge a battery with alternating current? You'd be
One-way diode, you can.
yes, okay. But if you just tried to use alternator, you'd be charging, discharging, charging, discharging, charging, discharging. You'd never get a charge because every half cycle changes direction. So in the old days, they used a split ring commutator, just like we were talking about before, but today you use a dual diode. Is that what you said?
One-way diode?
One-way diode. Well, a diode is one-way, yeah. But actually you use,
Oh,
yeah, okay, I got it. But don't you actually use two of them? It makes it more, three of them. Okay, it makes it more efficient. Okay, so you use that. They used to call them dual diodes. Now they use tridiodes, I guess. Okay, so what you have, your DC generator, is that every half cycle you flip it. Okay, and then move it again. So you smooth that out, and you have DC current. The sign of the current and the voltage is constant. The magnitude isn't constant, but the sign is. AC, they alternate constantly. Okay, it's not a constant thing. They alternate. So here is your generator. Now this time, you're not using electrical to make mechanical, you're using mechanical to make electrical. Okay? So again, you have a permanent magnet or something that acts like a permanent magnet, it may be electromagnet, with a fixed, and notice the field lines from north to south, always, they're this way. And you have something turning this, okay? Now, as you're turning this, right now, the maximum number of field lines are being cut. Half a turn later, how many are being cut? 0. You turn it another half turn, or a quarter turn, actually, and now maximum are being cut, but they're being cut in the other direction, and then it's 0 again. So this is making max, 0, min, max, 0, you know, it's doing that over and over and over. That is your induced voltage. Okay? Every one cycle you go through, you start somewhere, go through a max, 0, min, maybe back to 0. Just depends on where you start. So these are the connectors. So if something's turning your thing, and this could be water flowing through a dam, hydroelectric power. It could be a steam turbine, that a coal-fired fuel power plant, a natural gas powered power plant. It could be a nuclear power plant. You got steam turning a turbine. That's what's turning here. It's turning the coil in here, creating electricity. Generally, AC electricity, unless, of course, you put a split ring commutator on here. This time, when it's going this way, you're producing current, maximum current, one way, and as it turns, you know, your water, steam, whatever it is turning that. When you turn it that way, it goes to 0, and then right about the time it starts turning in the opposite direction, you flip from this side to that side, this side to that side, and now it's going in the same direction it was before, which would have been the opposite direction. So this is what makes a DC generator. And you get electronics to sort of even this out, smooth it out, but everything is plus here or minus. The induced voltage sign does not change. It's exactly like it was before, only before this went down here, now it goes up here because the poles changed. That's called a split ring commutator. Now we use. What's that? Okay, now the one you're looking at is probably that one, isn't it? Yeah. They don't show the second one. I don't know why. Okay? Now, all right. Let's move on. And they had one paragraph on generators in the book. One little paragraph. Surely should have had more than that. All right. Now let's talk about transformers. These are not those things that become people and cars, and that's not what we're talking about here in a direct sense, okay? Why do we need transformers anyway?
Step up and step down.
Why? Why do you want to step them up and step them down?
To get them from the power plant to your house.
Okay? What do you need then? It's going long distances. Okay, you need wire. And what happens in every wire? You lose energy. Because there's some resistance. Even the best conductor, as long as it's not superconductor, you're going to lose some energy. But what is it that loses the energy? What feature of it? The current. The higher the current, the more energy loss. The lower the current, the less energy loss. Okay? Now, as we said before, now this is sort of backwards. Okay, let's follow them. Problems in power transmission. High currents have high resistance losses because you got more coulombs bumping into everything else in there having resistance losses. Now, if you had high voltage, these are pretty dangerous potential differences because have a lot of potential difference between that, move a lot of charge. So, what's the solution? A transformer either boosts or lowers the currents and the voltages, but they do them in opposite ways. Okay? If you're boosting the current, you're lowering the voltage. If you're boosting the voltage, you're lowering the current.
Sounds like Ohm's law.
Yeah, well, it's not quite Ohm's law, but it's very similar to it. It's called the power law.
You got the same wattage in going out,
Okay, and what is wattage?
current and voltage.
Okay, yeah, it is that, but it's power, and what is power? Energy per time. So you have the same energy going in as you have energy going out. That is and they say power here, but it really would be energy too. That's the conservation of energy. You have the same power in as power out. The difference is some of this, like you said, power in is voltage in times current in. This is voltage out times current out. If you change one, you're going to change the other in the other direction. So when you're moving it from the power station to your house, that's a long distance. You want low current there so you don't have such high resistance losses. You want high voltage there, small current. So you get it there with minimizing the line loss.
And if you had high current coming from the power company, you would need a lot bigger wire.
You would need a lot bigger wire, have your things post closer together. Oh boy, it'd be a mess. So they do it that way. But then they don't want that high voltage coming into your house. Outside every one of your house, I bet, go out and check a power pole. You're going to find something that looks somewhat like that, and that's a transformer. It takes that high voltage, low current, and drops the voltage, that's a step down, raises the current so you can use it inside the house. That short distance from that to your house, minimum line loss there. You're not going very far. Remember, resistivity, there's three factors: length, diameter, you already mentioned diameter, and the type of material. Well, the material is your good copper wire, but the shorter the length, the less resistance you have, and the bigger the wire. And I bet you it's pretty good sized wire coming out of those two.
Yeah, put temperature in there.
What's that?
Temperature is in there.
And temperature is in there as well, right? But these are the ones affecting just that. Okay. Now, here is the basic formula for that. Since power in and power out, this is voltage times current, voltage times current. Okay? Now, what determines that, if you go back to your concept here, the more the number of coils. Remember that's the earlier slide, I'm not going all the way back there. The more the number of coils. Okay? So what you have here, now what they call on the inside is the primary side, the outside is the secondary side. So that's why it's P and S, not in and out. Okay? The voltage is to the number of coils, as voltage in secondary is the number of coils in secondary. The ratios are the same. That sets up a proportion, okay, a proportionality, okay? These are the voltages in the primary side, the input side, the number of coils on the input side, the voltage on the output side, output voltage, number of coils. I think they have a better picture. Here it is. Okay. basically you have one core here. Sort of, okay? And here's the input side, the primary side. Here's the output side. Okay. What's that? If you have 120 volts in with 10 turns here, okay? They got what?
They had their plug-in extension cord on the
I know, that's sort of backwards. So you can get
So
it.
it's stepping down.
Yeah, this is a step-down transformer because you only have one turn here, and the ratio, primary voltage to the number of turns, that's 120 to 10, as X is, or the unknown here, is to one turn here. So this 120 to 10 is a 12 to 1 ratio, so you have a 12 to 1 ratio coming out. So you step down to 12 volts.
10 to 1, right?
Yeah, what did I say? 10 to 1?
You said 12.
No, it's 12 to 1 ratio.
You got 120 in and 12 out, that's 10 to 1.
No, okay, that's the amount. So when I was talking about the ratio of voltage to coils, 120 to 10 is a 12 to 1, and 12 to 1 is 12 to 1. So the ratios are the same. Okay, now, however, if you had a 120 going in with just one turn, you had 10 turns here, what you got coming out? 1200. You got a really large voltage coming out. That's a step-up transformer. Okay? Now, that's only dealing with voltages. You go back to your power, though, and because the power in is power out, if this is 120 in and 12 out volts, that means the current here is 110, what the current is here. This is a large current out, a small current in, because it's a large voltage in and a small voltage out.
When you take the current and voltage on either side, power should be the same.
Yeah, so the power is the same. Power in equal power out. Yeah, exactly. Power on the second primary coil has to be the same as the power on the secondary coil. Okay? But that's a separate equation. So this one works voltage and number of turns, and then you use your power equation, voltage times current, equals voltage times current. If you drop the voltage here, you up the current. If you up the voltage, you drop it by the same factor. Does that make sense? Okay. Now, before we move there, let's do a couple of examples. Right here, we'll do them on this page. Got to have room enough to write. A step-up transformer has 5 loops on the primary coil. What were we calling that before? The number of loops in the primary coil, the equation just above that. What represented the number of loops? Say again? Okay, what was the symbol that we used to represent number of loops? In that equation just above that. Yeah, NP. And yeah, number of loops on primary was 5 loops. Okay? And 20 loops on secondary. What would that be? N sub S is 20. Okay? These are loops. If the primary coil is supplied with alternating current at 150 volts, so that would be, 120 volts, that would be, okay, but what symbol do we use there? Oh, VP, I see. Okay, got it. Sorry, I don't hear well. VP. And then what is the voltage of secondary coil? We're looking for VS. Okay? Do the math. How do you do it?
You take the number on the primary and number on the secondary, that's a 1 to 4 ratio.
Exactly.
And then take 120 and multiply times 4, and you got to
480 volts. That's exactly it. That's exactly it. However you set up the ratio, be sure you got the ratio. You can do them like this or like this, but just keep things corresponding to the right things, and you're absolutely right. It's a step-up transformer by a factor of 4. You're absolutely right. Okay? And that's what we got, 480 volts.
Their formula is kind of confusing.
Yeah, I know. I don't care for it either. Okay? But because the book has it this way, y'all bought the book, I don't want to change it. But yeah. Now, we just talked about what you do with the current. You go to the power formula, okay? And let's do example 610. Now, in my book, they've got something wrong here. Well, they have it okay because they said it the same way before. It just sounds strange. Yeah. So with an alternating current, which also means it's alternating voltage, okay? I don't like to call a current at 120 volts. That's not a measure of current, that's a measure of volts. But it's supplying an alternating current at 120 volts. So I just didn't like the way it read, but it's okay. But it's right. Okay, so primary voltage is 120 volts. Okay. Okay, I've got to find example. Oh, 6.9. Okay, got it. And a current of 10 amps. So that would be I sub P is 10 amps. Okay. And it says use the thing we just did, so this is going to be our VS. So how do we find out how much current comes through that? What is the current flow in the secondary current? We're looking for IS. That's the unknown. What formula do we use here? Yeah. But the one we've used is the power formula.
You calculate the power on your primary, and then you have 2 parts in your triangle, and you define current on your secondary side.
Okay. So what would you get?
So 120 times 10 amps is 1,200 watts.
Okay. What he's doing is VP IP is equal to VS IS. Perfect. And this would be 120 volts times 10 amps, and that's equal to 480 volts. No, okay, no, it's 1200 watts. Volts times amps is what? Yeah, I'm writing out the formula. 480 volts times IS. That's what I was doing. So then what you can do, and then
I got the 1200, I got the 480, I can calculate my current out of the power point.
exactly, that's what I'm doing here. I'm just doing it in one step and you did it in two. That's right. This would be 1200 watts is equal to 480 volts times your current, IS. Divide both sides by 480. Woo, I can't do it down there. If you got a calculator, 1200 divided by 480. $2.5. 2.5 IS is 2.5 amps. So if you jack up the voltage, you're decreasing the current.
And then that current ratio is 4 to 1 too.
Yes, and the ratio is 4 to 1. This is a 4 to 1. This has to be a 4 to 1, but in the opposite direction. If this is going up, this is going down. So take 4 and the 10. That would have done the same thing. I thought that's what you were going to say when you said I'd do it a different way. I said, show me. Okay.
Well, that was one of the ways.
That's one way. Right, exactly. Either way would work. All right, 2.5 amps. Very good. Oh, here's that swinging coils. On page 165, have a magnet down here, a coil up here suspended, another coil over here with a magnet below it. Absolutely no current anywhere. All you do is start this one rocking, this one automatically starts rocking.
Will they keep swinging?
They will keep swinging until one of them stops. I mean, friction is going to slow it down after a while, and then this will slow down too. But yeah, as long as this one moves out, it'll move. Yeah.
I was thinking you made
No, perpetual motion machine, dream on. Okay. If you keep pushing on it, it'll keep swinging. Okay. But you're adding energy. Okay. So there's your transformer, at least the first equation. The second equation came in when James did. Okay. By the way, all the folks who have come in since the very beginning, before you leave today, pick up your first and second test, because the last person to turn those in, turn them in on Thursday. So I got those graded, so I can return those to you. Okay. Any questions so far?
Question, James?
Second?
I was asking James if he had any questions on the
Okay.
figured part of this thing in there.
All right. Now, circuit connections. And basically, we've been talking about these all along. So let's give a little bit more. First, with alternating current, as I said before, most generated electricity, if a generator was involved, it came out alternating, unless you did something to make it direct, like diodes or split ring commutator or something else. Generators produce AC. Now, that's usually what's transmitted over your high voltage lines. They are step-up transformers to get high voltage, small current, step them down to use in homes or industry. With direct current, they were both right, Edison and Tesla. Both of these are necessary. Automobiles are DC machines, okay? You have a generator in there, but it has to convert that to DC. Using automobiles, cell phones, MP3 players, laptops, flashlights, anything with a battery, anything, solar cells, all those are DC. Now, the advantage of those, movable, portable. You don't have to be plugged into a wall, okay? The main current source is your chemical batteries, and like I said, this book does a really poor job on that, but we did talk about that briefly, okay? What you need for a chemical batteries, 2 dissimilar metals and an electrolyte to carry the charge, okay?
Can it be any two dissimilar metals?
What's that?
Can it be any?
No, not really. When I say dissimilar, they need to have different, and this is a sort of a technical term, different electronegativities, okay? If you have 2 different metals, but they have nearly the same electronegativity, that's not going to make a very strong battery, okay? But if you have 2 with very different, that's going to be a very strong battery.
So your pulse on your battery is not the same?
The post is just what you connect to, and a lot of times, at least on a car battery, I think those are lead, aren't they? The posts themselves.
They'll probably made them out of something else.
Yeah, they probably make them out of something else, but
They look the same. They look like they made out of the same stuff.
yeah, and I wouldn't be surprised. It's just some conductor. The post is just there to conduct the stuff that's happened inside. And on 12 volt, 9 volt, I'm sorry, not 12 volt, 1.5 volt, 8, AAA, AA, or 9 volt batteries or whatever. Really, the posts are about the same. They make them look different so you know which one's positive, which is negative. All right, now there's voltage sources in circuits. And this is what we did in lab. I really regretted that we were doing it before we really got to it, but y'all knew it well enough you could. And like I say, the labs are made up by the same people who did the book, but they just didn't do a real good job on that. They put all this, they split this part of electricity, that part of electricity, put magnetism in the middle. Why didn't they put this back in the other part? I'm not sure. Oh, and by the way, let me say this about transformers. What kind of circuitry do you use transformers on?
AC.
AC only, okay? And the reason for that, if you go back to this thing, what is it that creates a current? Oh, how soon we forgot. What creates a? Yes, a changing magnetic field. If this is an AC on this side, there's no way you can get anything here. It has to be changing here to change that. Okay? If you try doing this with DC. Now, a lot of people will talk about a DC transformer, and what they mean by that is a box like this. What they're transforming there is AC to DC. Okay? That's not what these transformers are. These are changing voltages and currents. This is changing.
That's really a rectifier and transformer.
Exactly. This is changing AC coming in, DC coming out, because these computers only run on DC. So they'll call this a transformer, but like you say, it's a it is transforming the type of current, but it's not this kind of transformer. It's not it probably is changing voltage and current some, but you know that's not the same thing. Okay, so here we're talking about voltage sources in circuits. Okay, and we talked about this in lab. Here is a series circuit of voltages, not series resistors, but series of voltages. In a series of voltages, what you do, you put negative, positive to negative, positive to negative, positive around to negative. You always connect them that way. What's going on in that circuit? Okay, what is added together? The voltage is added together. Very good. Let's just say this is 1.5 volts. That's what a lot of dry cell batteries are. So this would be 1.5 plus 1.5 plus 1.5. That would be a 4.5 volt battery. Okay. Now, the current is the same in that. Absolutely the same. Say again? Okay. So the current is the same. It's the voltage that is changed. And if you got 4.5 volts here, what's across here? 4.5 volts. Now, let me back off on that current. Okay. Let me back off on the current. It's the same current flowing through all the batteries. That's what I meant to say. Right. Okay. But if you have 4.5 volts here and whatever this resistor is here, you're going to have 3 times the current flowing across here because you have 3 times the voltage, and V is equal to IR. It's got to increase that way. If the resistance is the same, you increase the voltage, you increase the current. What I meant before was it's the same current flowing through all batteries.
All your voltage drops are equal to the source.
What's that? Yeah, the voltage up is voltage out. Yeah, right. Voltage drop. Exactly. So the total voltage is the sum of the single cell voltages. One current pathway, same current flows through the whole circuit there. Now, what if one of your dry cells shorts out? Yeah, it ceases to work.
If it opens, it kills the circuit.
It kills the circuit, exactly. That's why that single current pathway is sort of an important concept there.
If it shorts, it'll still work. You just won't work it'll be 3 volts. So if you short out one of those batteries, you're pretty much taking one of the batteries out of the circuit.
Exactly, right. That's what I meant.
But it's still a complete circuit because short.
Okay. So what you meant, what you understood about what I said, that if you just put a wire across here, you're taking this one out, then you have a 2 battery.
Yeah.
Okay, I see what you're saying. No, I meant the cell dies. If this one dies, or that one dies, or that one dies.
Well, the current is gone.
Yeah, the current's going. Yeah, because you got a single current pathway. Okay. What is this one? This is parallel on your batteries. Now, we didn't do one like this in lab. Okay, we didn't have the capability to. Okay, But a parallel batteries here, what's the deal here? Let's say this is 1.5, 1.5, 1.5. What's going across here? 1.5, because you got positive to positive to positive, negative to negative to negative. Hey, you got the same voltage across that. It's 1.5 volts anywhere. So what in the world would be the advantage of that system? It's what?
Getting the Kirchhoff's law.
Okay, not quite, but pretty close. What is happening here, you have a bigger battery. Not more voltage, but more amp hours. You got more total charge you could supply.
They do like when you build a stereo system in your car, or hydraulics or whatever, they have wild batteries.
Oh, is that right?
Parallel.
Okay. Well, what I was thinking, if, say, you had a remote weather station somewhere that you that didn't have power to it, and you had to supply batteries to it, and I would do a bunch of batteries in parallel to make it last a lot longer, because I don't want to climb up that mountain every other month and change the battery. I want them to last longer. So it's just like you have a bigger battery. Okay? You have 3. Same voltage across that. It's only going to supply a certain amount of current, but you have more battery life. Okay? All the negatives are connected, positive connected. The resultant voltage is determined by the largest cell voltage. So if this was a 1.5, a 2, and a 1.5, this would be 2 volts. These would just be supplying a little bit, but they would still do that. Okay? It makes greater electrical energy available. In other words, over a longer period of time. You increase the shelf life. Okay? Now that's if your voltages are in series or parallel. Okay? Let's now talk, this is what we usually talk about, series and parallel. This is what we did in the lab. If your resistances are in series or parallel. What is this one? Resistors are in series, okay? You got one, let's say there's 1.5 volts across here. You got 1.5 volts across there. And if those are all equal amps, what you got there? Half a volt drop, half a volt drop, half a volt drop. Exactly. You split your voltages, but guess what? Yeah, your current's the same through all of them, but this is actually less current than if it went just to 1 volt. Because then you'd have 1.5 volts here, or across one resistor, so you'd have 3 times the current. Okay. Now these bulbs would certainly be dimmer than one would, but your batteries don't last a lot longer because it's not supplying as much current. What a battery supplies is charge. Because what do we measure batteries in? You go to buy a battery, what? Not amp hours. Right? Look at the ratings of your batteries. They're amp hours, which means charge per time times time, that's charge. Your battery supply charge. And that's what you're dealing with here. The series connection of your loads, the total resistance is the sum of all the components. So let's say they weren't the same, or they were, it doesn't matter. You add this resistance to that resistance to that resistance, because you either triple the resistance or increase the resistance every time you put another one on. You haven't changed the battery, the voltage supply, so what you've done is drop the current. Okay? This is DC. Now if this was 120 volts, would you keep that? Yeah, what I'm saying. Okay. So the total resistance is the sum of the component. The current drops as more elements are added. So that's why our bulbs in the experiment we did got dimmer or brighter. Now this keeps showing electron current. I'm used to talking about conventional current, but they both work and mean the same thing. All right. So here is your formula for resistance. For series circuits, exactly. Series resistors. You add the resistances together. So R total. Now, I'm used to calling that effective resistance. I don't know if y'all call it that or not, or you call it total resistance. Resistance, okay. is R1 plus R2 plus R3, or however many you got. You add the resistors, and then you go back, figure out your voltage, and then figure out the current, because the same current has to go through them all. Now here is resistance in circuits, but you're going to do a parallel connection, like this. What's the, let's say this is 1.5 volt battery, so what's the 1.5 volts? 1.5? 1.5. So every one of those bulbs has 1.5 volts across it. So it's going to draw the same as if there's only one of them there, right? So what is going on here? Your voltage is the same, but what is the current? Yeah, the current is split, whereas in this.
That's when you get in Kirchhoff's.
Yes, exactly.
Current into it, that's when you get the same output.
Exactly. Okay, and then the loop law too. You know, that's the junction law. They also have the loop law. But the deal with this is this poor little battery is having to supply 3 times the current, because this is one resistor. If that's the same and that's the same, then the voltage is the same. So this is having to supply just as much current if these weren't there. That supplied just as much if those weren't there. This is just as much if those weren't there. So basically, I knocked my eraser off. Okay. So you have the poor old battery is having to supply 3 times the current. So which is going to last longer? This dry cell or that dry cell? The other one lasts a lot longer because these are going to be brighter bulbs. The other is going to be dimmer, but that will sure last longer. Okay. All right. More than one current path is available. What happens if you unscrew one of these bulbs? Just that one goes off, the other 2 stays on. What happens back here if you unscrew a bulb? All of them go off because the same current goes through them all. If you break the current, none of it. What's that? Christmas lights used to be. Y'all don't remember that, do you? Okay. But I remember my dad, every Christmas he'd pull those things out, and if they didn't come on when he plugged them in, the whole string went out. So you have to get one new bulb, and replace this one, and replace that one, and replace this one, and replace that one. If that didn't work, then do this with the second one, and then the third, until you got them to work. It was a pain. Okay. Now, so what's the total resistance of this one? 3 bulbs in series as opposed to 2 bulbs in parallel.
If they were equal size resistors,
Right.
they're a third.
Yes, your resistance, the effective resistance of the circuit actually goes down the more elements you put in. That sounds so counterintuitive. You put more elements in, your effective resistance goes down. Why? Because you're having to supply more current. Voltage stays the same. The current has to increase, so effective resistance is going down. Yes, it will drive you nuts, won't it? Okay. So the overall resistance drops, the more elements are added. The total circuit current increases as more elements are added. The voltage stays the same no matter how many you add. Okay. So in a series circuit, the voltage drops across each resistor. The voltages are the same across each in a parallel. The same current flows through all in a series. The currents add in a parallel. Okay? And your effective resistance in a series circuit increases the more you add. It actually decreases the more you add in the parallel. Okay. And unfortunately, there it is. Here is the formula for that resistance. And this is why I think of it as effective resistance. Yeah, this is a reciprocal relationship.
The way I do it, I put RT on one side.
And then you have,
I write all of that and then put 1 over all of that.
right,
Instead
okay,
of putting 1 over everything like that, that's kind of confusing.
yeah. And it's really tough to calculate. If you got a calculator with a 1 over x key on it, it makes it a lot faster, but you have to remember to do a 1 over x for your answer as well. Okay. So, it feels like there should be an example there, and yes, we do. Oh, we had one for, let me go back. Okay, let's do the one for series first. Well, let's see, isn't it just about time? Boy, stomach is controlling, isn't it? Okay, I think we're going to have to stop there. Ooh, that sort of messes things up. I had planned to finish this today.
FBI.
Yeah, actually it will work out all right. So let's back off from what was said before. This is how far we got today. It is time, isn't it?
Time to go home.
No, it isn't.
Back
Okay.
to Mississippi.
We just gonna go over there.
Yeah.
I mean, my point is right there.
Okay. So here's how the rest of the term looks. On Tuesday, okay, today for the rest of the day we're going to do Ohm's Law Lab. Okay. Then on Tuesday, when we get here, we're going to have finish chapter 6 and start chapter 8. But then when 2 hours are left at the end, then we'll have our last lab, the electromagnetism lab, for chapter 6. Then Thursday, we'll continue chapter 8, and for 2 hours, then the next 2 hours we'll just see how far we get in chapter 8. If we get far enough to do a lab, we'll do a lab. If we're not far enough, we'll continue in 8. But then we'll stop 30 minutes before the end and have the test on chapter 6, the last 30 minutes on Thursday, not Tuesday. Okay? Then the following Tuesday, which technically I think is the last day of class, we will, if we haven't finished chapter 8, we will, and then we'll have the lab on chapter 8, and then we'll have the test on chapter 8. Okay? The what? Okay. That's what I was going to get to. And we've got next week to decide. Okay? We'll either have pizza on that Tuesday or that Thursday. And we'll talk about that next week. Okay?
Yeah, let's do it on Tuesday. You should do perfect. We can have pizza.
Somehow I thought y'all would favor Tuesday. But we'll see.
Yeah, pizza came up the phone. We said, what?
Okay. Okay. So just a quick review. For the next 2 hours, we're going to do the Ohm's Law Lab. Okay? For then the Tuesday when we come in, we'll finish chapter 6, start on chapter 8, do that for 2.5 hour regular class, and then we'll have the electromagnetism lab the last 2 hours on Tuesday. Then on Thursday of next week, 1 week from today, we'll come in and just have 2 hours of class in chapter 8. Then we'll do the 2 hour lab electromagnetism. And then, no, I'm sorry. 2 hour lab, we'll get as far as we can in chapter 8. If we finish far enough, we will do the lab, but if not, the last 30 minutes will be the test on chapter 6. That'll be next Thursday. And then the following Tuesday, the last day of class, if we haven't finished chapter 8, we'll finish it. I think we will have finished it on Thursday. So we'll have the lab on chapter 8, the test on chapter 8, and probably have pizza. We can have pizza first and then have the lab and test. And then at that point, I will let y'all decide whether you want to take the final early or not. If you do, you can. If you want to come in on Thursday, you can take it then. In fact, you can take it anytime during that week. Okay? And I think I told you this earlier. I looked at the actual college calendar, and they said the last day of class for this class was the Thursday of finals week, with final being on Friday of finals week. And I did not think that would fly too well. So we're going to have the final on Thursday. Okay? Unless you choose to take it earlier that week. I'll give you that
Take it on
option.
a Tuesday?
Huh?
Can we take it on that Tuesday?
If we get everything else done. Yeah. Okay. All right. That said, I'm going to pause the recording. All right. Not all the way. Okay, with the lab set up, you got a resistor, you got a power supply, you got an ammeter in series with the resistor. Power supply basically is parallel with the resistor. And what you're going to do, as I said, I will tell you the voltages. So if you'll turn to data table 22.1 on page 197. Now you may not hit it smack on the nose, but aim for the following voltages. 1 volt, 2 volts, 3 volts, 4 volts, 5 volts, and 6 volts. Now some of these drift a little bit and other things, so get as close as you can to reading something close to those voltages and your ammeter at the same time, and then go. Now your ammeter, if you'll notice, I have these set to the 20 milliamp range. DC current, 20 milliamps. What you need to do is record that in amps. So give me a number that would be a characteristic number of milliamp. Milliamps. Something between 1 and 20. Okay? Something between 1 and 20. 2.3. Okay. So you see that, and that's going to be in milliamps. What you have to record is that in amps. And what would that be? Move it 3 decimals to the left. 0.0023 amps. Then you drop the milli, and that would have you amps. Does that make sense? Okay. So if you'll start doing, get as close to 1, 2, 3, 4, 5, and 6. Again, you may not hit it smack on the nose, but get it somewhere as close as you can to those values. Set your voltage, read your current, but record the current in amps, not milliamps. And when you're through with those, let me take a look at your numbers. Okay. And unless and until there's more questions, I'm going to pause the run of your graph. Okay, what did y'all get? Okay, you got a calculator? Ooh, problem there.
See your numbers.
See, I told you I was right.
That's what I was wondering.
How was it not?
Okay, and what were your 2 points? Show me your 2 points. The ones that you're doing your eyes are wrong from.
I counted 0.
Okay, what?
Yeah. You should have said find 2 points. I found the 2 closest together.
Okay, so you maximize your error that way, but let's see. So your rise here was 1, is that what you said? I see a 1 here, it was like 5.
Okay. So this I counted up 10 here and then over 12 here. That's how I got 10 over 12 here. So that goes from there, which is 0, to right here where we're running. You also got to think about it. This isn't a scale.
Right.
So much scale of 0.
So if you did it this way, rise was 1 and run was 0.012, right? If I'm reading that right. Okay. So 1 divided by 0.012. Got a calculator? What do you get? Okay.
That's ohms.
Ohms. Okay. Oh. What you got? Did you go? Okay. That and you're going here or
This is
you're going okay. So it'd be 6 over 0.073. See what that is. I'll just see. You got me there. All right. You got your. Okay, yeah, I thought that must be yours.
James
Okay.
thought it was.
Okay.
What is it, a 100 ohm resistor?
Yeah.
To calculate error, don't you put the, actual resistor on top and then,
Okay. Let me find the page. Here it is.
you divide, right?
Okay, let me see what they're asking for to make sure.
Result from
Okay. Now, by the way, folks, since you've done your calculation, every team gets something. Okay, I heard they got about 83. You got what? 104? What did y'all get? Did you get anything? What was your slope? Did you get slope? Did you get numbers? Yeah. Okay, what were they? Pretty much. Okay. So what you do is subtract this minus that. This minus that. That's 5 divided by this minus that. Okay. Now, they're still cranking there. Okay, you calculated your slope. You say write it on page 194 and somewhere on the graph. Done that?
What are we writing on 194?
Page 194, results number 1, calculate the slope and write it here and somewhere on the graph. Write it in between 1 and 2 and somewhere on the graph. Okay? Then number 2, compare the calculated value of the known resistor, that's what you got, with the accepted value as given by your instructor, 100, and calculate the percent error. So let me show you how to do percent error.
You put the 104, you put our
Okay.
number on top.
Okay, what you do is the error, which is you had 104, y'all had 83.3 or whatever, divided by the actual 100, okay, and then multiply by 100%. So that was, I'm sorry. 104 minus 100 divided by that. Now, if y'all have 83, you put 83.3 or whatever minus 100 divided by 100. And that will give you your, multiply, make it a percentage. Did y'all get a number yet?
83 minus 100 divided by 100, and you still multiply that by 100%.
No. Yeah, divided by 100, then yeah.
It would really be 4.1.
Yeah. And this way is pretty easy. That's 4%.
We got negative 17.
Negative 17%. Exactly. And usually anything within 15 is about normal. Okay, so you're not far off. Did y'all get a number? Yeah.
Negative 17%.
Y'all should have close to
Negative 17%.
Okay. What's that?
So what kind of
Okay, and so your error is 4.6, and divide that by 100, you get 0.04 or 0.05, something like that. No, the number is multiply by 100, you get 4%. 4.6%. Yeah, 4.6%. Okay. Now, that's your known resistor. You calculated percent error. Okay. It's what? No, yours is 4%. Right? 100. 4 minus 100 is 4. Divided by 100 is 0.04. Times 100 is 4%. 4%. Yeah. Get it into a percent. 4%. And anything around 15% or better is good, so yours is not bad. All right. Now, what you're going to do now is the new resistor.
On the x-axis,
Okay? And you go back and do the same thing.
Where do you put the, you can't check.
You like it?
You want
You see
better?
number 1 on page 194, whatever. Yeah, yeah. Slow down on the number 1. Okay. Y'all got new resistors. And this time y'all calculate what it is. I told you what that was. You tell me what this is. Not by the stripes. What's that? Okay, they got the new resistors now.